Alrighty. Hello, everybody. Oop, I'm going to get my slides going right. There we go. Thank you for joining us today. Good morning, good afternoon, good evening, whatever parts of the world you're in. Welcome to this third part of a series. We're going to talk about the CAP theorem here. I think of the first two parts I was in Denver. This part I'm in New York City. So as with everything, we're all over the place in this world today. So, but all the more reason you need partition tolerance in your system. So let's get into this. Before we get started, please do ask questions in QA and in the chat. I'm joined by my friends Michael and Jeff today from our team, and they'll be happy to answer any and all questions that you have along the way. At the end of the webinar, we will conduct a really quick survey. Please help us with your feedback. It's really critical. We take it very seriously. JP, my partner in all things kind of live stream and webinar here at Cockroach, and I go through these things with fine tooth and check it all out and make as many changes as we possibly can along the way. A lot of the things that we've done thus far has come from direct feedback from you, the audience. So thank you for that initially. And then finally, as always, a recording will absolutely be available after the event. So no need to ask that one in the chat and QA. We will definitely make this available. It's typically within an hour or two or so up on our on the Cockroach Labs YouTube channel. And I think the very first two sessions of this are already up there. They were up there. They've been up there for a while. And thanks everybody for joining me for those, and then for this one as well. But oh man, my slides are really touchy today. My name is Jim. I'm Jim Walker. I'm in product marketing here at Cockroach Labs, and have been with the company for about, oh gosh, almost 3 years, just over 2.5, I guess. I'm an ex-engineer. I was electrical engineering, computer science. I majored in computer engineering in undergrad at UIC, University of Illinois Chicago, which I think is the best school ever. But then again, I went there, but I haven't coded in quite some time. I'm pretty curious though, and I love these things, and we'll get into that in the next slide. If you want to follow me or comment on anything that happens here or any of the other live streams on Twitter, I'm just @James. Okay. So this session is, I would say, intermediate to beginner. It's going to be not as advanced as the last two sessions, and that's just really the nature of the topic, honestly. And I think we'll get into that, and you'll see very quickly kind of how partition is a little bit different than consistency and availability in the CAP theorem. I'm not a distributed systems expert. I work with a lot of incredible distributed systems experts, so I glean a lot of information from them. I'm curious. I love this stuff. And honestly, I just feel that the concepts that were outlined in this series, and JP, again, thank you for kind of originating the concept here of actually going out and doing the series on CAP theorem. I think this is just really important stuff that's changing the world that we live in today in lots of different ways. So this is the tech that's really driving the future of where things are going. So what we want to do in this series was really give kind of this high level kind of context around this very important concept. So like I said, this is part 3 of a 3-part series. We held a session on consistency, about a month and a half ago. Availability was about a month ago, and then there's been a bit of a delay between the last two and this one. Thankfully, it's been an interesting, busy time here at Cockroach Labs for sure. But the other two videos around consistency, availability are both up already. I think the consistency session was fantastic. We talk a lot about Raft. We talk about multi-version concurrency controls in there. I think in the availability one, we talk about how we can, auto shard and place replicas of data across, multiple different servers. And I think those two sessions are a little bit more technical than this one, because ultimately, I think that the power of the CAP theorem comes back into really the concepts of consistency and availability, where, partition tolerance is a little bit different. It is kind of an adjunct concept and basically a foundation for all these things. And I think if you read about the CAP theorem, the more and more you read, it becomes very, very very apparent that partition and partition tolerance is a little bit different. So let's give a quick recap. I did this in the last session as well, so that if you were kind of standalone, just coming into this fresh, you have a little bit of a history, right? And so, I'm a child of history. I really quite love history of computing. Honestly, I think it's intriguing. The amount of time between the beginning of all this and where we're at today, and the changes that have happened in our society that we as technologists have kind of made happen are just truly phenomenal. And it really goes way back to, I like to think about Fairchild Semiconductor as the beginning of this. That was really the genesis of Intel and all of our 8086 architectures and what Motorola did there, and then bringing that to market with the PC and everything that's changed in our lives. Truly phenomenal. But the treacherous eight, the guys who took off and started Intel, truly remarkable. Palo Alto Research Center, if you live in the Bay Area, Park Place, I was lucky enough when I first started coding to code in a language called Smalltalk, which came out of the Palo Alto Research Center. Same thing with the mouse and the and Windows for that matter. And that was early days of Xerox. And I think that a lot of the shift in terms of kind of these innovative research center type things, I would be remiss without talking about digital and DEC and everything that's happened there. But also, I think a lot of work has been done at IBM as well over the years. And I think they did carry the torch really until I would say the early 2000s, when I think, the shift towards distributed systems and the shift towards this, massive global compute and how we think about systems today really started at Google. I remember when Google first started, they're like, wow, how do they innovate? And they're just a simple search engine. It's just one line and that's all it was, right? And we had Alta Vista and Lycos and Yahoo, and it was a crowded market. Well, Google realized very quickly that if they can outpace the innovation on the back end, they could outpace those other search engines, and they surely did it. And I think a lot of what we're looking at today, the CAP Theorem included, if you look at NoSQL databases, a lot of the things that have changed our lives and our society kind of have come out of Google over the past 15, 20 years. There are two engineers at Google. If you don't know who they are, I would highly suggest you read this particular paper. It was in Wired. But if you look at Jeff Dean and Sanjay Gamawat and the stuff that they've actually invented, the papers they've published as part of the publications at Google. I think it's google.publications. Look at them up, and if you look at these two guys, there's some really amazing stuff here. MapReduce, which was kind of the beginnings of big data and how we actually think about distributing compute and these sort of things. The back end of Hadoop, if you will. Bigtable, kind of the beginnings of NoSQL. The Google file system and everything that's meant for just large scale storage. Spanner, which is very near and dear to our heart here at Cockroach Labs, because the Google Cloud Spanner is really kind of the genesis of CockroachDB. A lot of the principles we're going to talk about today really were outlined in that paper as well. And then if you think about what they've done in ML and AI and TensorFlow, their involvement in Kubernetes. And I think these two in particular, and not just them, but everybody that surrounded them at Google in the 2000s really kind of transformed the way we think about things today, including my three employers, friends of mine, Peter, Ben, and Spencer here. They were about employees in the 300 range. I think Peter and Spencer helped build out Colossus, which was like the next generation of Google file system. But they saw basically Bigtable and Megastore and Spanner be built, and they had a front row seat, and they were interacting with those teams. And what they had there was a set of technologies that they wanted to build a company on. But once they left, they didn't have that technology, and that was really kind of the start of CockroachDB. And oh gosh, Ben and his instrumental work in Google Reader as well, which was another large project. There's another large kind of big person at Google, and I think right now, Eric is a Google fellow, and he invented something called the CAP Theorem. And here he is actually with the founder of the internet. Oh, no, this guy's vice president was the founder of the internet, right? So this is way back in the day. But Eric Brewer really kind of came up with this theorem, and actually the CAP Theorem was originally called Brewer's Theorem. But Eric was, deep entrenched in search and everything else, and in distributed systems. The Brewer's Theorem, first appeared in 1998. There was a debate around acid versus base. If you're not familiar with the concept of base, it stands for B is basic availability, soft state, and then eventually consistent. You can imagine that. I think there was this emergence of this move towards NoSQL, and base being the kind of new principles, whereas acid was the original principles in which we built database and data systems off of. There was this emergence of this new concept, and there was a debate around that. And I think the staunch attachment to acid not invalidated, but I think people they thought Bayes was too disruptive, right? They were just kind of against it. And so the CAP principle was first published in '99, and then in 2002 it was actually proved as a theorem by, I believe Seth and Nancy were both PhD students at MIT at the time. But if you want to go back and actually check this out, it's some really interesting stuff. But the concepts around the CAP theorem have been with us for about 20 years. Building large-scale systems off of these principles, that's a wholly different function and a wholly different challenge, right? So ultimately, so that's a quick recap and a quick history of everything, right? And so ultimately, the CAP theorem really states it's impossible for a distributed data store to simultaneously provide more than two of the following three guarantees. Consistency, every read is going to receive the most recent write or an error. Availability, every request is going to get a response. And then it needs to be partition tolerant, right? It's going to continue to operate despite an arbitrary number of things being dropped out of the system. Now, if you think about those three things, consistency, right? Data is going to be right. Availability, I'm going to get an answer at all times. And then partition tolerance, well, the concept of being distributed really comes back to partitions. And so I think, originally when we thought about these three things, there's this combination of the P with consistency and partition with availability, but just a flat out, the partition thing is a foundational element. If we look at consistency, as we noted, it's two requests being made from two different sources against two different nodes are always going to return the same amount of data. It just means that data is going to be consistent everywhere we go. So no matter who's accessing from whichever node or whatever endpoint you want to, you're always going to get the same exact data come back, right? Oh, and by the way, yeah, I think there is some question. There's a question that already came through. Yeah, more and more parameter comments all three, and that would be decision. Interesting. So actually, somebody's proposing a fourth concept in the CAP theorem in our chat, and I'll come back to that in a little bit, Jayakar. Okay, but consistency is really kind of as simple as this. Availability is basically saying if you ask one of the nodes, you're going to get a response. Now, is that response going to be consistent all the time? Will it be eventually consistent? Are you going to be guaranteed that when you ask for one thing, you're going to get the same thing everywhere? You're not going to get that. I like to think of like consistency as our traditional relational databases where we can tune isolation levels so that we can guarantee that nuclear codes and financial transactions are going to be right all the time, right? That's actually pretty damn important. Whereas kind of availability really is this push towards, if you think about these eventually consistent, the base principles that we were talking about and some of the NoSQL databases, right? And I think, they err on this side of availability, but ultimately what it really comes down to, and the foundational element behind both of these is really that things are partition tolerant, right? If two requests are made from different sources against different nodes, and these nodes are disconnected, the system will continue to operate. And really, I think of partitions as, and why did we even call it partitions? I think there's two principal qualities of a partition. It's number one, it's something that will go away. You have many of them in the system. This comes back to, this is a distributed system. So is this a node? Is it a communication channel? What is it that we're actually trying to survive? Is it, of a distributed system? Think about the DNS as a distributed system, right? etcd is a distributed system. There's lots of different kind of examples of these, but each one of those kind of pieces being a partition in this. And when I think about partition, it's not just the thing, it's also a period of time, because the time of the tolerance, right? The tolerance part of partition tolerance actually is pretty important. And can you survive a minute of a partition being gone? Can you survive 5 milliseconds? Can you survive an hour? Or can you provide reliable transaction quality across any one of those, any one of those kind of combinations thereof? And so when I think about these things, I typically think of not just the thing that is involved, but also the period of time that actually is participating in as well. So to me, the partition part of CAP theorem is really the heart of scale out distributed systems. This is why we actually have the CAP theorem, is because we want to build for scale, right? We want to build for resilience. I mean, these are the the core principles in which we actually build distributed systems. And I think, as developers, as builders of the next generation of IT, I really feel that these are the things that are going to be the most important for us to work into our systems. And I think this is what the engineers at Google and lots of other kind of leading edge companies have done over the past 15 years. They don't think about building scale around the system. You think about building it into it. You don't think about designing for resilience in the architecture of where the thing is going to sit. You actually build it into the system itself. If you want to talk a lot about scale and resilience, I think in the first two series, we did talk about in the availability one for sure, how we were able to scale at a database, auto shard. We think about sharding as a way of getting scale with the database. So we can attain this horizontal scale, right? How do you actually do that inside the data? Let the database just deal with that. And that is the difference between kind of applying it to a legacy machine or a legacy system and actually building it into it. And that's where, if you start to do these things inside it, it becomes a distributed system. Now, distributed systems, in my opinion, are difficult. And it's these consistency, it's the availability, and it's being tolerant to these partitions going away. And I think that's the trick behind all this stuff. So I think, doing these things internal is a big deal. Now, partitions happen, and there's massive, huge effects on systems. And I think about it, if you think about it at the top level, if something goes down, from an availability point of view, number one, loss of a transaction, loss of data, loss of any sort of interaction with the customer, loss of a customer for that matter, if you're going to lose something, right? That's one way in which it will affect your system, right? But I also think, and more importantly, is this partition recovery. If I have, one state and at some point a partition starts and I'm in some mode where changes are happening and then I come back from this partition being recovered, well, how do I resolve and remediate the differences between kind of, think about it as two trunks or two threads here. And I think this is one of those systems and one of those things we think about in the availability of systems when we think about kind of like active passive systems, this sort of thing. This is the stuff that's really difficult to deal with. And so it will affect your system. And so what's the importance and what is the impact of this partition recovery on your data and your workload and what you're trying to solve for? And I think that's the questions we have to ask as architects of next generation software. What's important for me and my app? And choosing the right data system from a distributed systems point of view is just critical in that decision. I think this is an architectural conversation a lot of the times. I think, as developers, we have to think about these things, especially as, the distributed nature of these things actually becomes very important. I always like to think about, when we used to deploy databases, you just think about the logical model, right? You think about tables and rows and columns. You think about referential integrity. You think about, the data types, these all the the DML is pretty simple at that point. When you get distributed, you have to think about the physical nature of data as well. And the physical nature of data is really what's going to affect really the plausibility of what we design and the overall applicability to the problems that we're solving. You can't divorce the business logic from the distributed nature of the workload anymore. Now, there's a great article, actually. Eric Brewer came back to the CAP Theorem. It was published in InfoQ, I believe in 2013, 2014 time range. So, it's 12 years later. This is a great article. If you really want to actually catch up in terms of like a lot of the things that we're talking about right now, but you want to read it in a better way, look at, like I said, I'm not an academic. I'm just a marketer. I read a lot though. And, I think this article in particular, that was published at InfoQ is a great read. It's a bit cranial, but I think it will help you really get into the head of distributed systems expert. And I think getting into distributed systems and learning Raft and learning MVCC and learning how we can use these things to say auto shard or build in resilience into our systems, I think this is what's going to separate expert programmers from just regular programmers in the very near future. So I think this is really great stuff. So I would go out and check that out. It's actually a really, really good piece. So, ultimately, the CAP theorem says it's impossible for a distributed data store to simultaneously provide two of these three guarantees. Right? Ultimately, when we think about this, we wouldn't think of a CA database. That, you know, typically we'll think about CP or AP or whatever that is. A CA database just basically eliminates the need to be distributed. It's not going to be a distributed system if you eliminate the partition tolerance part of this. I think of something that's consistent and available as a single instance of Postgres, a single instance of MySQL. You don't have partitions that you have to survive the failure of, right? You can tune it as long as you have access to it through that one endpoint, and you can tune it for the highest level of consistency, whatever you want. And so I think the concept of a CA database is not what we think about when we think about distributed systems, because it's just simply not partition tolerant. What we do think about is the AP databases, right? Available and partition tolerant. I think this is what happened over the past, 15 years with the inception and the delivery of all the NoSQL databases, like the Mongos, the HBases. I mean, even Cassandra to a point, right? I think it's an AP database, right? Where you're going to have availability of that data, and it's going to be partition tolerant. But are you going to be guaranteed, consistency within that database? And I think there's certain workloads that are correct for those types of databases, but of course there's certain workloads that you want to be consistent and partition tolerant. This is the likes of Spanner. This is CockroachDB. Some of the other distributed SQL databases that are out there are kind of moving in this direction. How am I distributed and built for the cloud, yet still guaranteeing, these transactional workloads that have been wrapped up in things like Oracle and DB2 for all these years, right? How do you deliver, for us, serializable isolation so that, data is always going to be correct? And so to me, that's a CP database. And we definitely err on that side. Now, that said, my final point, and I think we've made this a couple different times in some of the other sections, consistency and availability isn't a trade-off. It's not one or the other. It's not binary here, y'all. It is really, you can spend a whole lot, you can tune, you can play with the system. And so ultimately, I think you can peg yourself on, let's say, I want to guarantee consistent, but I'm going to be able to get damn near close to 5 nines availability for my system as well. And there's lots of ways that you can do that by tuning the database or looking at the features of the database, right? Performance becomes a very big piece of this as well. Delivering consistent transactions at global scale across, nodes that are in Singapore and New York and guaranteeing availability to that data, that is just not simple stuff to do. And, kudos to this engineering team. Like I said, I am just, elated that I get to work at Cockroach, to work with some really interesting people. But there's a lot of technology out there that allows us to get damn close to, being fully available, being fully consistent. And I think, these are the things that you have to look at. Now, for you and your workload, it's trade-offs of what you want to actually do. If data isn't guaranteed to be consistent, that's okay for your workload, right? It's not nuclear codes. It's not financial transactions, right? So do you use a NoSQL database for something like that? Possibly, yeah, right? Like, it just depends on, do you want the elegant nature of the relational schema, right? Or do you want to use JSON, right? There's lots of different kind of characteristics that go into these decisions. And it really, really ultimately comes down to what you want to do with your workload. All things being tunable, all things being spend enough money, spend enough time, you can get to where you need to be. And I think that's the lesson I've learned really off of kind of going through this whole process of, diving deep into the CAP theorem, diving deep into Cockroach and distributed systems. I think that's some of the trick that I think about. So I'll leave you kind of with one thing. I'm gonna come back to this question. It was actually a really good question. I would love to hear other people's opinions on this, but there's a couple things that I feel are really, really important to understand, especially around distributed systems. Go learn about Raft. If you don't want to learn about Raft, go learn about Paxos. Both of them, distributed consensus algorithms, extremely valuable, and I think really, really important to help move your career around into distributed systems and really be a practitioner of these things. We talked about MVCC, multi-version concurrency control, another key concept. We use it for the concepts of consistency. That was in the very first webinar that we did. Thinking about replicas of data in the context of Raft and how to distribute that data. Again, really, really important stuff. So I think these are all kind of core concepts. There's been a lot of stuff throughout this series, lots of links, lots of places to go read and study. I hope that this has been valuable to you all, just from a high level introduction into some of these concepts. And And I hope I've given you some great pointers of where to go and study more on these things. And, we'll absolutely make the slides available. I know Hesham was asking in the QA, and, the first 2 videos are already out there. You could listen to me in twice the speed if you want to, if you don't want to listen to me in full time, but we'll get this one out there as well. And I hope this was valuable to you as well. Again, this is a little bit of a weird session relative to consistency and availability. This is kind of I'm happy we're doing this one last, because ultimately it's kind of the foundation of what I think of as really. And then finally, I think if we, what happened? Oh, good, I'm good. Finally, if we think about, if you want to go use Cockroach implements a lot of these things, y'all. Cockroach Cloud is available off our website. We actually have a free version of a serverless version of Cockroach Cloud that we're building that you can go out and use today. So that's my one commercial in all these things. I think we've stayed pretty fair in terms of being cockroach free, I guess, a little bit. So so with that, I know there was a question here, and I don't know if Michael, are you on as well too? I don't know if you want to talk about this or not.
Yeah.
Yeah, there was a challenge about CAP theorem, and can it be challenged if we add one or more parameter common to all 3, and that may be decision. What do you think of that? Like, what do you think of when you see that question, Michael?
Maybe it means now we can make a decision on which version we want to use and consider to be the actual reality or truth. Like, do we want to choose to take the most recent one, or is that, I don't know if that's the nature of the question that Jayakar posted.
Yeah. I actually struggled with it as well. I was kind of waiting it to the end so I can actually think through that. But I think, somebody was asking if I could share the links again. Yeah, the links are there, y'all. I think when I think about decision, I think about, personally, I'm not sure where that goes in terms of like how it actually, if it's CAP D, if that's a thing here. I kind of agree with you, Michael. It's one of these things where, you have to make decisions in what you want to architect and what you want to build, right? And I think you're dealing with that all the time with customers, right? They're going through these conversations.
Right, but then that puts the responsibility onto the part of the app developer and also the team as a whole to implement that in a consistent way. Whereas if you choose to go with a database that's consistent, then you don't need, I guess it's just the trade-off, like you said at the beginning of, for certain applications, we might choose to be available. For others, we might choose consistency. So I guess at that point, it could be a business decision as well.
Yeah. Well, Jayakar did clarify a little bit. So decision on the event of time. And I think time is a critical piece of all this, Jayakar. And I think when you start thinking about consistency, time becomes a really important thing, right? And I think that is why I think when I think about partition tolerance, the amount of time that's out is really, really important as well. So I'm not sure if we answered your question perfectly, Jayakar. But we're happy to get in a conversation about that anytime. Like I said, I think these are the great conversations we all have to have about our systems and what we're building today. So I'm a study of this. I love this stuff. So Michael, thank you again for helping out here. I really appreciate it. And thank you to everybody for joining. For all of you who joined for all 3 of them, gosh, kudos to you. You listened to me 3 times through these things. But I do hope this is available for all of you. We'll make sure to get all the videos will be up. The slides will be available. But please do take the post-event survey. So there's one last question here. What insights did you have when you thought of making Cockroach Labs a CP database? That's a great question somebody asked. And I'll go back to a little bit of the history around Cockroach database to answer this question before we just sign off here. And Peter, Spencer, and Ben, definitely Peter and Spencer were at another company. They were starting a company. They just didn't have the tools that they had at Google once they had left. And they looked at things that were out there and they said, man, I could use these NoSQL databases. They're just not getting the consistency guarantees that they needed for the app that they were building. They wanted Spanner. And I think really what it comes back to is they wanted to, they needed a relational database. They needed something that was going to give them the serializable isolation and consistency guarantees for their workload. There was nothing out there. There was no open source database that was doing this. And so their decision of making this a CP database was really built off of that. And it's, this is what's outlined in the Google Cloud Spanner white paper that we referenced earlier. And I think, it's building that, but divorced of kind of Google hardware and available for everybody was really the decision, so that lots of companies could use this sort of database. And I think that's where this is headed today. So let's see here. Michael, there's a couple of questions here. And I know there's a couple of there was a couple of questions here about how do people dial in availability, but then tune out consistency. I think the first two
that was me.
We didn't talk about that.
Sorry, Jim. It was me.
I know. Funny, like I can't carry. It's why we actually made this 3 parts, was because it's just too complex to do in a single session, So right. I think that's far. But there was a question from YouTube. I don't know if you want to take this, Michael. What helps determine the impact of running nodes in a geo-distributed deployments? Is it mostly network link latency and throughput, or is there anything else? Like, what is the, I mean, that can go in lots of different places, right? I mean, we have these conversations, correct?
Yeah, I mean, that's kind of one of the neat things that, with CockroachDB, we've taken that into account, is that the database itself, when you have a multi-region system, it's always measuring what is the latency between all the different nodes from one to the other. And you're able to basically tune your latency by using our multi-region constructs, to optimize for the latency that's acceptable to your application, so that you can still run a multi-region application and have acceptable latency. And so I guess I would urge folks on that topic to look up our multi-region. Didn't we do a multi-region session recently?
Yeah, I think about a month ago, and it was like there's main features around 21.1, and I think I love the question because it comes back to the speed of light, right? Like, we're never going to beat the speed of light, but what do you need to accomplish in the context of the speed of light? And I think that the link latency, understanding those concepts is actually pretty important in distributed systems.
But we're kind of bending light, you could say, exactly, in a way.
Right? Well, we aren't bending light, but maybe we can change the photons, right? And so I think that the trick here is how do we, how do you design the database, and how do you design your physical data model to accomplish what you want to accomplish? Do you want, data to be accessible very fast, but lower from a consistency point of view all over the planet? Or do you want to make sure it's going to be consistent and very quickly accessed in one region? Say, I want all German records to live in German. And so how do you do that at the database layer, at the table layer, and then at the row level? And I think being able to think through your data in all those different ways is where, a distributed database is very, very different. And I think, just using a distributed database isn't like you're going to be some distributed systems expert. I think it just takes time to get used to things like this, right? I mean, you see our customers go through this all the time, right, Michael? It's a little bit of they go through these kind of phased approach, right?
Yeah, and there's also a really interesting article that we might throw out there now. It's Living Without Atomic Clocks. That blog post was really good as well. So
that's right. And by the way, I would be remiss if I didn't mention our documentation. I do that every single time I'm on one of these. So if you really want to see the life of a transaction in Cockroach, there's some really good material there as well. So let's see. Yeah, I think we covered everything here. If there's something that is in the chat I'm not totally grokking, and I want to make sure I'm able to answer. Sorry, but we have answered everything here, Michael. So we did it in 40 minutes. I was going to do 30, but I think we did a good job here. So thanks again for helping me out, Michael.
Yeah, you're welcome. Thank you, Jim, for having me on.
I haven't spoke to you in a couple weeks, so it's always good to hear your voice, buddy. So.
And you're in New York now, and not Colorado. It's amazing.
Well, exactly. I get around, right? So. Again, thank you everybody for joining us. All 3 parts of this series are available. I would highly recommend checking out the consistency part of this. Really, really interesting stuff there. I had a whole lot of fun building that one out, and the availability session as well. I hope you found this one useful, this session useful as well. This is, like I said, a little bit of a different topic in the concept of CAP Theorem, but I think important to be complete across the 3-part series. So. With that, thank you everybody for joining. If there's any other questions, gosh, please reach out, DM me, James at Twitter, send me an email, jim@cockroachlabs.com. I'm happy to take on any and all questions from anybody. So, and I'm happy to actually discuss these things with people too, because I find it to be intriguing, and I'm, like I said, a bit intellectually curious on all these things. So thank you everybody for joining the 3-part series, and we look forward to seeing you on our next session. See you, Michael. See you, everybody.